Hello everyone. Here I'll be presenting our work on TCP throughput over full-duplex wireless local area networks, novel implications of the AP's new capability. This is an extended version of the talk presented at ICC 2024. In conventional wireless networks, the devices are half-duplex. In other words, they can transmit or receive data but not do both simultaneously. For example, in the figure on the left, the access point is half-duplex. In the first time instant, it is receiving data from an uploading station, and in the second time instant, it is transmitting data to a downloading station. On the other hand, in the figure on the right, the access point is full duplex capable. Therefore, it is receiving data from a station and transmitting data to another station simultaneously and over the same frequency band. This promises to double the spectral efficiency of half-duplex wireless systems. The power of the signal that the AP is transmitting in the downlink is many orders of magnitude greater than the power of the signal that it is receiving in the uplink. Therefore, the signal that the AP is transmitting causes self-interference at the receive antenna of the AP. However, in the literature, it has been shown that with sophisticated analog and digital signal processing techniques, up to 80 to 100 dB of self-interference can be cancelled, making FT possible in practical scenarios. Here we take a look at the FT-aware 802.11 MAC protocol. Initially, all the nodes, that is station A, the AP, and station B are all in backoff. At some point, station A's backoff timer reaches 0, and it sends an RTS packet or a request to send packet to the AP. After a short interframe spacing or SIFS duration, the AP responds with a clear to send or a CTS packet. After another SIFS duration, station A transmits its packet to the AP, which happens to be a TCP data packet that station A sends to the AP with rate R1. While receiving a packet from station A, the AP sends its own packet to another station, station B, at rate R2. After the SIFS duration, station B responds with a MAC layer ACK to the AP, acknowledging the successful reception of the AP's packet. The AP sends a MAC layer ACK to station A, acknowledging the successful reception of station A's packet. These MAC layer ACKs are sent together and are sent a TCS duration after the end of the longer transmission, which in this case happens to be the AP's packet, which is a TCP data packet sent at rate R2. After a distributed interframe spacing or TDIS duration, all the nodes resume their backoff timers. While the MAC layer throughput implications of FT are well studied in the literature, what is less understood are the implications of FT on transport layer protocols such as the Transmission Control Protocol or TCP. First, let's understand the TCP Congestion Control Protocol. In TCP, the data packet flow is regulated by the congestion window. The congestion window is the maximum amount of unacknowledged data that can be present in the network and is an indication of the amount of congestion in the network. For example, let's consider a server that is connected to an access point and that is using the TCP transport layer protocol to transmit packets. The server looks at the current congestion window value and injects packets into the network, that is, into the AP's MAC queue, only if the amount of unacknowledged data in the network is lesser than the current congestion window value. The congestion window is updated based on the TCP ACK reception. TCP ACK packets are packets that are sent by the receiver to the sender in a TCP connection, acknowledging the successful reception of the data packet. In the slow start phase, the congestion window is aggressively updated and it doubles in every round trip time. In the congestion avoidance phase, the congestion window increases by 1 in each RTT until it finally reaches a maximum value. In the analysis presented in this paper, we are operating in the regime in which the congestion window has reached the maximum value. Now that we understand the basics of the TCP protocol, let's look at why we study TCP over Wi-Fi. For this, let's consider a station that is downloading data from a server which uses the TCP protocol. The server is connected to the access point via a wireline link. The server first breaks down the data into multiple TCP data packets and sends it to the AP via the wireline link. The AP sends this data packet to the downloading station via the 802.11 wireless channel. This generates TCP ACK packets at the station, and the station sends these TCP packets over the same 802.11 wireless channel to the access point. The access point then sends this TCP ACK packet to the server via the wireline link. So, both the TCP data packets and the TCP ACK packets for the same TCP connection are sent over the same shared 802.11 wireless LAN contention-based MAC. So the AP and the station are contending for the same channel for the same TCP connection. This can lead to delays in either the data packet or the ACK transmission, and these delays due to the MAC contention can lower the TCP throughput of this connection. Our goal is to analyze the TCP uploading and downloading throughputs and to characterize the cross-layer interactions between the FD Wi-Fi MAC protocol and the TCP protocol. In doing so, we'd like to account for the two new challenges that turn up while analyzing TCP throughput over FD Wi-Fi. The first is cross-link interference. Consider a scenario where the FD-capable AP is receiving a TCP data packet from one uploading station while simultaneously transmitting a TCP ACK packet to another uploading station. The transmission from the uplink transmitting station interferes with the signal that the other uploading station is receiving from the AP. This causes the signal to interference plus noise ratio, or the SINR, at the downlink receiving station to reduce. The AP thus has to reduce its data rate to make sure that the downlink receiving station can successfully decode its packet. The second new challenge are the asymmetric payloads. In the same scenario, the uplink transmission is that of a TCP data packet, and the downlink transmission is that of a TCP ACK packet. The TCP data packet is much longer than the TCP ACK packet. This leads to asymmetric durations in the uplink and the downlink that can cause MAC layer inefficiencies. These two challenges need to be accounted for in our cross-layer analysis. Let's look at the system model. Our system consists of both uploading and downloading stations, and we use the RTS-CTS based enhanced FD MAC that we discussed before. We have a server that is connected to the access point via a wireline link. We have ND downloading stations and we have NU uploading stations. Let's look at the TCP data packet flow for both the uploading and downloading stations. First, let's look at the downloading station. Each downloading station is downloading a large TCP file that is present in the server. The server breaks down this file into many data packets and sends it to the AP via the wireline link. The AP then sends these TCP data packets to the downloading stations via the Wi-Fi channel. This generates TCP ACK packets at the downloading stations, and these downloading stations send the TCP ACK packets to the AP via the same wireless channel. The AP then sends these TCP ACK packets to the server via the wireline link. Each of the uploading stations has a large TCP file intended for the server. It breaks down this file into many TCP data packets and sends it to the AP over the wireless channel, which then sends this packet to the server via the wireline link. This generates ACK packets at the server, which sends it to the AP via the wireline link, and the AP sends these TCP ACK packets to the uploading stations via the wireless channel. These are some of the assumptions you make about the TCP congestion control model that are typical of most analysis of TCP over HD Wi-Fi. The first is that we assume there are no packet losses or TCP ACK timeouts. Secondly, we assume that the undelayed ACK mechanism is used. What this means is that each TCP data packet generates one TCP ACK packet at the receiver. Conversely, each TCP ACK packet acknowledges the successful reception of one TCP data packet. Lastly, we assume that there is negligible delay between the server and the AP. This applies to some widely implemented TCP congestion control versions such as TCP New Reno and TCP Cubic, since in the absence of loss events, the TCP congestion window grows to the maximum value and stays there. Our analysis is based on mean field and renewal theory. We use the mean field based decoupling approximations to analyze the Wi-Fi MAC. The first decoupling approximation states that the backoff process of any node is independent of the aggregate backoff processes of all the other nodes. The second one states that each attempt by the AP or an STA undergoes a collision with a probability that is independent of the number of retransmissions or independent of the number of collisions experienced so far. We also introduce a new FT-specific saturation approximation that states that the AP and all STAs always have a packet to transmit in their MAC queue. This is a significant departure from the analysis of TCP over HD Wi-Fi, in which the stations are assumed to have at most one packet in their MAC queues, and it is shown that most stations do not have a packet to transmit with a high probability. We now validate our FT-specific MAC saturation approximation. In TCP over HD Wi-Fi, the AP is the bottleneck, and most of the packets reside in the AP's MAC queue. Thus, as mentioned before, the stations have at most one packet in their MAC queues. The number of active stations, or in other words, the number of stations that are contending for the channel at any given point, is much lesser than the total number of stations n. However, in TCP over FT Wi-Fi, the AP is no longer a bottleneck due to its FT capability, and the AP and all STAs always have a packet to transmit in their MAC queues. Here we plot two figures which are the histograms for the number of contending stations in TCP over HD Wi-Fi and TCP over FT Wi-Fi for a system with n equal to 50 stations. In the figure on the left for TCP over HD Wi-Fi, we see that the number of active stations is never more than 3. However, in the figure on the right for TCP over FT Wi-Fi, we see that the number of contending stations is n equal to 50 with a probability of 0.97, thus validating our FT-specific MAC saturation approximation. Here we look at the expressions for the aggregate downloading and uploading STS TCP saturation throughput. We use the renewal reward theorem to arrive at these expressions. The numerator is the mean reward and the denominator is the mean renewal duration. The reward for the downloading STS throughput is LD when the AP successfully transmits a TCP data packet during an interval and is 0 otherwise. The AP's HOL packet or head of line packet is a TCP data packet with probability H. H is given by ND divided by N. The AP can be successful as a primary transmitter, which occurs with probability beta AP times 1 minus gamma AP. Over here, beta AP is the probability that the AP attempts an RTS packet transmission, and gamma AP is the conditional collision probability of the AP. In other words, it's a probability that the AP's RTS packet will collide given that it has attempted an RTS packet. The AP can also be successful as a secondary transmitter, which occurs with probability n times beta STA times 1 minus gamma STA. Here, beta STA is the attempt probability of an STA, and gamma STA is the conditional collision probability of an STA. This term, that is n times beta STA times 1 minus gamma STA, represents the additional transmission opportunities that the AP gets because of its FT capabilities. The denominator, expectation of T, is the mean renewal duration. Similarly, for the uploading station's throughput, the reward is LD when one of the uploading stations successfully transmits a data packet. This happens with probability NU times beta STA times 1 minus gamma STA. And the mean renewal duration expectation of T remains the same. Now let's look at the expression for this mean renewal duration. From the decoupling and saturation approximations, the time instants when the backoff timers are decremented are the renewal instants. The renewal duration T is a random variable that depends on whether a success, collision, or idle event has occurred. An idle event occurs when none of the nodes transmit an RTS packet in that interval or slot. The probability of this happening is 1 minus beta STA to the power of n times 1 minus beta AP, and the renewal duration during an idle event is delta seconds. A successful event occurs when either the AP or one of the STAs successfully transmit a packet. The probability of the AP successfully transmitting a packet, as mentioned before, is beta AP times 1 minus gamma AP, and the probability of one of the stations successfully transmitting a packet is beta STA times 1 minus gamma STA. Depending on the nodes involved in the uplink and the downlink, the renewal duration during a successful interval can vary because of the asymmetric uplink and downlink packet durations and the asymmetric payloads of the TCP data and TCP ACK packets. A collision event occurs when one of the nodes collides with another, and the probability of this happening is 1 minus the probability of an idle event occurring minus the probability of a successful event occurring. And the renewal duration during a collision interval is TRTS plus TDIFS, which is the time duration to send an RTS packet and a diffs interval. As mentioned before, the renewal duration during a successful event depends on the nodes involved in the uplink and in the downlink. If the AP succeeds in accessing the channel, it is the sole transmitter. Therefore, the renewal duration T is TPR1 if the AP transmits a TCP data packet and TAR1 if it transmits a TCP ACK packet. Here TPR denotes the entire duration needed to send a packet of length LD bits at rate R. It includes the RTS duration, the CTS duration, the 5 preamble duration, the duration needed to send a packet of length LD bits along with LH header bits at rate R, the MAC layer ACK duration, and all the CIFS and DISFs intervals in between. Similarly, TAR is the entire duration needed to send a packet of length LA bits at rate R. If a station succeeds, the renewal duration is TPR2 if a downloading station sends a packet to the AP and the AP simultaneously sends its packet to a downloading station. Similarly, the renewal duration is TPR2 if an uploading station is transmitting to the AP and the AP is simultaneously transmitting to a downloading station. The renewal duration T is TPR1 if an uploading station is transmitting to the AP and the AP is simultaneously transmitting to another uploading station. And finally, the renewal duration is TAR2 if a downloading station is transmitting in the uplink and the AP is transmitting to an uploading station in the downlink. These different renewal durations during FT transmissions occur because the MAC layer ACKs are sent TCIFS duration after the longer transmission. Over here in this slide, we are showing the two cases where the renewal duration is TPR2. As you can see, the longer packet in both these cases is a TCP data packet sent at rate R2. Similarly, in this slide, the figure on the top, the longer packet is the TCP data packet sent at rate R1, which an uploading station is sending to the AP, and therefore in this case the renewal duration is TPR1. And in the case where TCP ACKs are sent both in the uplink and the downlink, the longer packet duration is a TCP ACK packet sent at rate R2 by the AP, and therefore the renewal duration in this case is TAR2. We now look at the effect of the number of STAs on the TCP throughput. In this figure, the total TCP throughput, that is, the sum of the aggregate downloading and uploading STAs throughput, is plotted against the number of stations n, where n varies from 20 to 80. For FT, both analysis and simulation results are plotted, and we see that they match well with an error less than 5%. This validates our analysis and the approximations that we make. We also plot the TCP throughput for two different values of FUPL, where FUPL is the fraction of uploading stations that is given by NU by N. For FUPL equal to 1 by 4, we see that the total TCP throughput of FT is 41% higher than that of HT. And for FUPL equal to 3 by 4, we see that the total TCP throughput of FT is 54% more than that of HT. Here, we look at the effect of the cross-link interference on the TCP throughput. In this figure, the total TCP throughput is plotted against the fraction of uploading stations FUPL, and FUPL varies from 0 to 1. For FT, the TCP throughput is plotted for three different values of R2, R2 equal to 36 Mbps, R2 equal to 27 Mbps, and R2 equal to 12 Mbps. The greater the cross-link interference in the network, the lower rate the AP needs to use in the downlink, since the downlink receiving station needs to successfully decode the AP's packet in the presence of this cross-link interference. For R2 equal to 36 Mbps, we see that FT achieves throughputs that are 26 to 50% greater than that of HD as FUPL increases from 0 to 0.65. For R2 equal to 27 Mbps, see that FD achieves throughputs that are 5% to 48% greater than that of HD as FUPL increases from 0 to 1. Interestingly, for R2 equal to 12 Mbps, we see that FD is actually detrimental to the total TCP throughput when FUPL is between 0 to 0.65. This is because for a low R2, the transmission durations can be longer than that of HD, and this can negate any gains that FD can provide. We also see that as FUPL increases, the effect of the crosslink interference reduces, or in other words, the effect of this CLI limited data rate R2 decreases. This is because as FUPL increases, the transmissions are dominated by uploading stations sending TCP data packets in the uplink and the AP sending TCP ACK packets in the downlink. These are of duration TP-R1, which is not a function of R2. Finally, these are the conclusions. We analyzed the TCP throughput over an 802.11 FD wireless local area network. In doing so, we captured the interaction between the TCP protocol and the IEEE 802.11 contention-based FD MAC protocol. We saw that additional FD transmit opportunities led to the AP and stations being saturated with a high probability, which is significantly different from TCP over HD Wi-Fi. We saw that despite the increased contention between the stations, despite the asymmetric payloads of the TCP data packets and the TCP ACK packets, and despite the different uplink and downlink rates due to crosslink interference, FD achieved significantly higher TCP throughput than HD. Some interesting avenues for future work include modeling the effect of packet losses and delays, and also modeling the delayed ACK mechanism in the TCP congestion control protocol. Thank you.